Hello, I'm Patty Simpson with Simpson Math. Let's solve inequalities. First, let's just start with the basics. Here are some different symbols that in math represent those different inequalities. So this symbol means less than. This one means greater than. I remember that this one's less than because it's the same direction as an L goes. And this one then is the greater than. But the mouth, maybe you've also seen that the mouth eats the bigger number. So here, since it's pointing at the smaller number, this is less than, and this symbol is greater than. When we add the line underneath, then it means less than or equal to. It can be less than the number, or this part means equal to that number. So this is less than or equal to, and this symbol means greater than or equal to. So let's practice reading using those symbols. So this particular sentence says 3 is less than 7. And this one says 7 is less than 3. Let's see if we can put our own symbols in the sentence to make it true. In this case, our 18 is greater than 15. So we need to use that greater than symbol. Maybe you learned that Pac-Man eats the bigger number. So we can use that greater than symbol. So that Pac-Man is eating that 15. In this case, 54 is less than 81. So again, when we put that symbol in, we want to put in the less than, or our Pac-Man again eats the bigger number. So there's some basics about our inequality symbols. We're going to practice now using those symbols and putting a solution on a number line. So let's just read these different sentences first. This says that x, so some number, is greater than 7. This one says that some number, our x, is greater than or equal to -6. This one says our x is less than -1/4, and this one says our x is less than or equal to 2. So what does that mean? We're going to draw a picture that kind of shows what our x values can be. So when this says that x is greater than 7, think of some numbers that x could be. Could be any number that's larger than 7. So maybe the x is 9, or maybe x is 25, or maybe x is 1,000,000, or maybe x is 7 1/4. As long as it's some number bigger than 7, it would fulfill this requirement. It would make this sentence true. So we're going to show on a number line all the different values that x could be. We're going to put all those different values on here: 7 1/4, 9, 25, 1,000,000. So we're going to show them all on this number line. And the way we're going to do that is, we've got a number line counting along there: 5, 6. The important one is 7, because that's what's in our inequality here. And we know that our x value, well, it could be 8, it could be 9, it could be 10, but it could also be 9 1/2, or 7 1/4, or 8 1/8. So it could be any of those numbers. So to show that, we're going to say, hey, look, our value could be at 9, or it could be at 8 1/8, or it could be almost, it can go all the way down 7.000000001 is bigger than 7. but it cannot be 7 itself. 7 is not greater than 7. So to show that it gets really, really, really close to 7, but it isn't 7 itself, we're going to put an open circle right here. But it could be any other value that is larger or greater than 7. And to get out there to a million, we're even going to color that arrow to show that our solution is anything on this side of 7 our x value could be. So this just visually shows us on a number line what this says, that x can be anything greater than 7. And here, that's what this shows us, is it can be anything greater than 7. We're going to show our solution of this one, where we have x is greater than or equal to -6. This is kind of that same idea, where we're walking along on a number line. We're at -9, -8, -7, -6, and just walking along. The important number that we need on our number line is -6, because that's what's in our sentence. And again, this says it can be bigger than -6, so it could be any number that is larger than -6. It could be -5, it could be -1, it could be 25, it could be 1,000,000. It could even be -5, -5 halves. Or it could be something that is in between here. It could be fractions. So to show that, we're going to color everything larger or to the right of that -6. This time though, it can be equal to -6 because -6 is equal to -6. So to show that, we're going to put a dot at -6. So this dot means it can be equal to -6, and then it could be anything larger. So the difference between just a greater than symbol and a greater than or equal to symbol is the greater than symbol has an open circle, where the greater than or equal to symbol has a closed circle. And it's because it can be that number. That could be a solution for my x. On this side, we have less than. It's the same idea, that our values for x could be anything smaller than -1/4. And we know that smaller numbers are to the left. The smaller we go, the more we go to the left, the smaller the numbers are. So we could show that. On our number line, when we're drawing the solution, what's most important is to put on the number in the sentence. So I need to put -1/4 on my number line. I could put other numbers out there as well, 1/2, 3/4, maybe I've got 1/2, -1/2, -3/4, -1. Need to put some other ones maybe out there. Then, because it's less than, I need to color everything that is less than that -1/4. Then it's not equal to it. So to show that it's not equal to it, it can get really, really close to that -1/4, but it can't be -1/4 itself. I'm going to use that open circle. One last one. This one is x is less than 2. 2 is bigger, so I'm going to color everything smaller or to the left of 2. So again, I need to make sure that 2 is on my number line, because that's the important number we're dealing with here. This time, because it can be equal to 2, I'm going to put a closed dot there at 2. And then I'm going to color everything to the left of that 2. Now, a lot of students realize that the direction of the symbol is the direction we are coloring. So when my x is is less than, then we're coloring it to the left. And when my x is greater than, then we're coloring it to the right. But you do have to be careful. That's only true if my x value is on the left. However, I could write this same sentence like this, where 7 is less than x. These two things say the same thing. If x is greater than 7, then that means that 7 is less than x. In this case, notice that when I have my x on the right, the side that I colored does not go the direction of my arrow. So I have to be careful about which way I'm coloring it. One thing you can do to check yourself, to check to see if you've colored the right solution, is to pick some number that you've colored, like 10, and plug it in and see, does that work? Is Pac-Man eating the right number? So if I put in 10 in there, yes, 10 is greater than 7. So that would make sense. So you can always check just by picking a number and making sure that it actually makes the equation true, or the inequality true. Now let's look at doing different operations on both sides of an inequality sign and see if it continues to make that inequality true. So let's start with adding on both sides of an inequality. Here I have the inequality 10 is greater than 5. We all agree that 10 is greater than 5. So what I'm going to do is I'm going to add 2 to both sides of my inequality, and let's just see if this is still a true statement. So I'm going to add 2 to both sides of my inequality. And when I add 2 to both sides of my inequality, I end up with 12 is greater than 7. That's still a true statement. Well, what about if instead of adding a positive 2 to both sides, what if I decide to add a negative 2 to both sides? Let's just see. If I add a negative 2 to both sides, is it still going to make this equation true, or inequality true? See, I have negative 2 plus 10, or 10 minus 2 makes that 8. And on this side I have 5 plus a negative 2, or 5 minus 2, which makes that 3. 8 is greater than 3. So with inequalities, I can add a number to both sides of my inequality, and everything is still true. Let's look at subtracting a number from both sides of my inequality. So this time I'm going to subtract a number from both sides of my inequality. Let's subtract 4 from both sides of the inequality, and let's just see if that remains a true statement. So I have 10 minus 4, which is 6, and 5 minus 4, which is 1. 6 is greater than 1. So subtracting something from both sides, my inequality is still true. What about if I subtract a negative number? So let's say I subtract a negative 4. So 10 was greater than 5, and I subtract a negative 4 from both sides. Well, we know this negative and this negative really just makes that positive. So we end up with 14 is greater than 9. So, and 14 is greater than 9. That is a true inequality. So we can add numbers to both sides of our inequalities. We can subtract numbers from both sides of our inequalities, and everything is fine. Let's try multiplying both sides of our inequalities. Let's multiply both sides by 2. And let's just see what happens when I multiply both sides by 2. Well, 2 times 10 gives me 20. And 5 times 2 gives me 10. 20 is greater than 10. So multiplying by that positive 2 was fine. It didn't change my inequality by multiplying both sides of the inequality by 2. Let's try multiplying by a negative 2. If I multiply both sides by a negative 2, negative 2 times 10 gives me a negative 20, and 5 times negative 2 gives me a negative 10. Which one of these is larger? Oh no, negative 10 is actually greater. So if I put in this greater than symbol, that's not a true statement. When I multiply both sides of an inequality by a negative number, it causes a problem. And actually what we have to do to make our inequality be true when we multiply by a negative number is we have to flip our inequality. So anytime we're multiplying both sides by a negative number, we have to flip our inequality. I'm going to write that down. When multiplying both sides by a negative number, the inequality sign flips. So addition's fine, subtraction's fine, multiplying by a positive number was fine, but multiplying by a negative number, we have to flip our inequality. Let's look at division. First, let's divide both sides by a positive number. 10 divided by 5 is 2. 5 divided by 5 is 1. This is still a true inequality. 2 is greater than 1. Let's see what happens though when I divide both sides by a negative number. So I'm going to divide both sides by a negative number. 10 divided by a negative 5 gives me a negative 2. And 5 divided by a negative 5 gives me a negative 1. Is negative 2 greater than negative 1? No, negative 2 is to the left of negative 1. It is not bigger than negative 1. This is not a true inequality. So again, when I divide by a negative number, I have to flip my inequality. So when multiplying or dividing both sides by a negative number, the sign, the inequality sign, needs to flip. We're going to solve equations or solve inequalities, and we can do the same things for solving inequalities that we do when we're solving equations. We can add a number to both sides, we can subtract a number from both sides, we can multiply a number to both sides, and we can divide a number by both sides. But when we multiply or divide by a negative number, we must flip our inequality sign. Now let's solve some inequalities. Let's find what values would make what values for x would make this inequality true. So we're going to pretend that this is just an equal sign. The only time we have to do something different is if we are multiplying or dividing by a negative number. Then we need to worry about the sign and flip it. Otherwise, we're going to do exactly like we would if it was an equal sign. So the first thing we do if there's an equal sign is we simplify on both sides of our equation. We're going to do the same thing here. If we can simplify on both sides of our inequality, we're going to do that. but we can't combine unlike terms, so there is no simplification here. After we look for that, then we look to get our x's on the same side of this inequality, just like we would if it was an equation. So I'm going to move my x value from the right to the left. And remember, the way that we move that is we zero it out. Right now, it is minus x. I want to add x to both sides, so that when I add x to both sides, on the right, this becomes 0. Then on the left, I have 3x plus 9. Notice that on the right, the x went away. I made this 0 so that when they added together, it became 0, and 6 plus 0 equals 6. So now all my x's are on the left-hand side of this inequality. Now, just like if it was an equation, I'm going to look for that guy that's not clinging, and I'm going to move him. I'm going to make a 0 here to move him to the right. So right now he's a positive 9. If I subtract 9 from both sides of my inequality, then I'm going to, again, make a 0 here. That makes that 0, and it leaves me with 3x is less than or equal to a negative 3. Excuse me. Then we need to divide this number 3. He's multiplying right now, and the inverse of that multiplication is a division. So I'm going to divide both sides by 3. I am not multiplying or dividing by a negative number. I'm just dividing by a positive 3. So I don't need to worry about flipping the signs. If I were dividing by a negative 3, then I would have to worry. So even though the numerator is negative, it doesn't matter. It's only if I'm dividing by a negative, then I have to flip the signs. Here I have x is less than or equal to, well, negative 3 divided by 3 is a negative 1. So my x value could be anything below 1, a negative 1, could be anything less than negative 1, or it could be negative 1. And that would make this equation true. First, let me put that on a number line. Remember, when we're putting it on a number line, that the important number that I put on there is the number in my inequality. So I need to have negative 1 on the number line. And then, because it's equal to, I'm going to put a filled in dot, and then it's less than, so it's anything to the left of that negative 1. Just to check myself, I'm going to pick some value that is less than negative 1. Let's say I pick a negative 4. And I'm going to plug that negative 4 in, and I'm going to test to make sure it's true. So if I put a negative 4 in, 2 times negative 4 makes negative 8. 9 plus negative 8 is 1. If I put a negative 4 in here, a negative of a negative makes that a positive. So 6 plus 4 would be 10. And 1 is less than or equal to 10. So negative 4 does make that statement true. So after you've found your solution, you can check yourself to make sure that your solution actually works. Let's solve another one. Again, pretend for a minute that it's an inequality. An equality, an equal sign. The only time we have to worry about it being inequality is if we multiply both sides by negative or divide both sides by negative. We want to simplify first on both sides. So I'm going to ignore the right-hand side and just look at the left-hand side. I can combine these like terms over here on the left. I can combine this 2x and that x. 2x plus x makes 3x. And then I have the minus 3. Then on the right, I can distribute this 5 so that I have 5x, 5 times x, and 5 times 1. Well, 5 times x is 5x, and 5 times 1 is 5. Once I have each side simplified, then I want my x's on the same side. And I can put my x's on the left, or I can put my x's on the right. For this problem, I'm going to move the -5, but you could move the -3 either way. The way I move that -5 is I want it to make a 0. So I'm going to subtract 5x from both sides. When I subtract 5x from both sides, on the left, that leaves me with a -2x minus 3. This makes 0, plus 5 is just 5. Now all my x's are on one side. Once I have all my x's on one side, I look at that side with the x's, and I look to see anybody who's not clinging to the x. And I get rid of him by zeroing him out. So this one is subtracting 3. The inverse of subtraction, or minus, is to add 3. So I'm going to have a -2x on the left, plus 0, which is just -2x. 5 plus 3 makes 8. Next, I need to divide off that -2. Oh, but alarm bells should go off when I'm dividing by that negative. Remember that when I divide by a negative, so this time my number on bottom is a negative. When I divide by a negative, this sign is going to flip. So I end up with 1 times x, which is just x. 8 divided by a -2 gives me a -4. Now, I'm going to put that on a number line, show our solution there on a number line. Our x value can be anything that's less than 4. So when I'm putting it on a number line, that -4 is the important number to include on my number line. And then it's not equal to it. Since it is not equal to -4, I'm going to put an open circle there because it can't be a dot at -4. But it's everything that gets close to -4, super, super close to -4, and then anything to the left of it because it is less than. Then to check myself, I could pick a number like -7 to put into this equation or inequality to see if it works. So if I put in a -7, everywhere I see that x. On the right, I have -14 minus 3, 14, 15, 16, 17 is -17 plus a -7. I keep going into negative land, so I'm at -17. That's a -24. So now on the right, if I put a -7 in there, then I have -7 plus 1 makes a -6. 5 times a -6 makes a -30. Sure enough, -24 is bigger, it's on the right of -30. So putting in this value does make that inequality true. So you can check yourself at the end by choosing one of your values to put into your inequality to make sure that it's true. And when you divide by a negative, you have to remember to flip that sign. We'll solve a couple more. This one has a fraction in it. We learned a strategy for dealing with fractions where we multiply both sides by the least common denominator. In this case, there's only one denominator, that 3. I'm going to multiply both sides by 3. So I'm going to multiply this side by 3 and that side by 3. On the left, I need to distribute that to both terms. So I'm doing 3 times 8, and then I'm doing 3 times this 1/3 x. On the right, I just end up with 3x. On the left, I have 24. And remember, the reason we do this is because this 3 and that 3 become 1, and I'm just left with 1x, or just x. Now I don't have to deal with the fractions. Maybe you don't mind dealing with fractions, and up here you added 1/3 x to both sides. That works, you could totally do it that way. I just like to get rid of my fractions, and this is a strategy for doing that. Now, I want my x's on the same side, so I'm going to add this x to that side. I add x to both sides of my equation. I end up with a 24 is less than or equal to 4x. Divide both sides by 4, and because it's positive, just like because I was multiplying by a positive up here, I'm dividing by a positive here. I do not have to worry about flipping the sign. So here, 24 divided by 4 is 6, is less than or equal to 1x. Now I'm going to graph this, but maybe before I graph it, I'd like to turn it around. 6 is less than or equal to x is the same thing as saying x is greater than or equal to 6. Notice here that Pac-Man is eating the x. The greater than or the less than sign is the x is greater than the 6. I need to make sure that that Pac-Man is still eating the same number. Then when I put it on my number line, 6 is the important number to put on my number line. And then, because it is equal to this time, I'm going to fill in the dot. And then x is greater than or equal to 6, so that means it's anything larger than 6. Again, I can take some number that's out there that's larger than 6 to plug in for x. Let's say 9. 1/3 times 9 is 3. So 8 minus 3 would give me 5. And 5 is less than or equal to 9, which is what I used. So my solution, I could pick any of those numbers out there and they should make that work. One last one. Again, we want to simplify on both sides. On the left, there's nothing to simplify, but on the right, I can distribute my values so that I end up with negative 4x minus 14 on the left, and on the right, I have 4. A negative 2 times 3x makes that negative 6x. A negative 2 times a negative 1 makes that a positive 2. I can continue to simplify there on the right by adding my like terms. So my left stays the same, but on the right I have 4 plus 2, which is 6, minus 6x. Now that I've simplified, I need my x's on the same side. So I'm going to move my x's, move these 6x's to the other side by adding 6x to both sides. When I do that, it leaves me with 2x minus 14 is less than 6. look at the side with the X. Anything not touching it, not clinging to it, we're gonna get rid of. So we're gonna add that 14 to both sides. So I end up with 2x is less than 20. Divide both sides by a positive 2, so I don't have to worry about flipping the sign. And x is less than 10. So again, on that number line, my important number would be 10. It's an open circle because it doesn't have the equal sign, and x is anything to the left of that 10. So anything left of the 10, less than the 10, could be a solution to this problem. So when you're solving inequalities, it's just like solving with an equal sign, an equation. The difference is when I divide or multiply by a negative number, I do have to flip my sign. Then I can, just like in an equation, I can check my solutions to make sure that they actually work. Math Made Simple is some math. Thanks for watching.